A different thought process here that we're going to have to get into is a little bit about constraints and statical determinacy. And this is like talking about what statics can give you. What can you get out of statics? And let's look at this structure right here. We have a pin support, and then a roller, and then a roller, and then we have an applied loading at a 30-degree angle. Okay, so this is a given loading, and then we have 1, 2, 3, 4 unknowns. The pin support has 2 unknowns, right? It has an X and a Y component. This roller only has perpendicular to the ground surface, so a vertical and then a vertical here. So we have 3 equations of equilibrium, standard for 2D. Sum of forces in the X, sum of forces in the Y, and sum of moments about the Z about a point. So we could sum moments about A, or some moments about B or C or whatever. But we really only have 3 equations of equilibrium, and there are 4 unknowns. And I don't know what you know from math, but you cannot solve a system that has too many unknowns for the equations of equilibrium. Now, this example here is kind of a neat one because it's not that you can't sometimes get some of the reactions when it's indeterminate. It's just that you're not going to be able to solve the whole thing. For example, here we could calculate RAX because these are parallel and perpendicular to RAX. So RAX is the only support in here that's going to be able to resist the 1.7 kips as it's pushing to the right. So if we did 1.7 kips times cosine of 30, that's how much this point right here is getting pushed to the right. You know RAX is actually going to be pushing to the left. It's going to be opposite the direction of this arrow, and it's going to be that value. Okay, so yeah, we can find some values sometimes, but in general, if you have too many unknowns for the number of equations, it is indeterminate, which means statics will not determine it for you. Okay, so you have a redundant constraint or more, one or more redundant constraints. So redundant constraints means you have extra, and the amount of that you have extra, we call that the degree of indeterminacy. That's not really important too much right now, but if you have 2 extra supports, it would be statically indeterminate to the 2nd degree. This one here is statically indeterminate to the 1st degree because we have 1 too many unknowns. Okay, a problem is statically indeterminate when it has more unknowns than equations of equilibrium. And the system usually cannot be solved using these concepts of statics, which is a bummer because that's, what's the name of the class that we're in? Statics. So if you have this, even at the end of the semester, you'll be like, I learned all this stuff. I'm the boss now. I understand it. This problem you couldn't solve using statics. I can't solve it using statics. Statics doesn't give you enough information, doesn't give you enough equations. There are ways it can be solved, but it's using the concepts of strength of materials, so it's beyond this course. Are statically indeterminate structures used in practice? What do you think? All the time. There's probably more statically indeterminate structures in real life than there are statically determinate structures in real life. Your house, the walls in your house have studs every 16 inches. You cannot determine what the axial compression is in each one of those because it is a statically indeterminate system. We have way too many studs in there. Why do we do that? We do it because the studs, the redundancy is good, right? If you're putting in a new electrical switch for your, you have one switch in your electrical box, and you want to add a ceiling fan to have a separate light and a separate fan switch on there. So you want to go and you get a reciprocating saw, and you cut and you're extending that opening over a little bit, and you cut through a stud. Whoops, didn't mean to do that, did you? Does the whole house come crashing down? No, because it's statically indeterminate. If you take a statically determinate structure and remove a support, then you have collapse. But statically indeterminate means you can remove one of these and you're still good to go. It's going to behave differently, but it's still not going to collapse, which is really cool in real life. So a lot of things are statically indeterminate. The problem is, again, statics alone can't get you the answer. There's also unstable or partially constrained. And what that means is you don't have enough reaction. So here we have a pin support over here. It's got a vertical reaction and a horizontal reaction. We have that 1.7 kip load applied at 30 degrees. Yeah, we could calculate what these two should be equal to, right? Some moments about A equal to 0. You don't get it equal to 0. That's the whole problem, right? These two vectors pass through A, so they would not cause moment about A. The vertical component of this 1.7 kip force would be pushing down over here, and this whole beam here would swing down and crash, like a hinge falling down because it's unstable or partially constrained, meaning we don't have enough statics vectors here. Here we have 3 equations of equilibrium still, right? And we only have 2 unknowns. When a body does not have enough support reactions to hold it in equilibrium, it becomes unstable and collapses. A problem that is partially constrained has fewer unknowns than equations of equilibrium, and the system will not be stable. That's really a problem. So are there many structures out there like this? Not for long. They're the ones that fall down. So this is where you're going to live in this semester in statics, is in statically determinate. It's like, it's like Goldilocks and the 3 bears. The first one, statically indeterminate, was the porridge was too hot, and then unstable was the porridge was too cold, and this one is just right. Okay, here we have 3 equations of equilibrium like we always have, and we have 3 unknowns. 1, 2, 3. Boom. We can solve this system. No matter what, we've got it using statics. And so that is statically determinate. When we have exactly enough support reactions, it is statically determinate. Okay? Even sometimes with these, though, you can have a collapse mechanism even though the equations and the number of unknowns match. Okay? There's just a couple of special cases for it, so it's not that big of a deal. Here's one case. We have 3 equations, 3 unknowns, but all of our reaction vectors are parallel to each other. Now look at this force vector that's applied. If we had a force vector applied just vertically, that's great. Okay? Think of a skateboard, right? Skateboard's got a wheel at each end, and you stand in the middle. If you get on the board by standing straight on top of it, the board stands, and you can sit there standing on top of the skateboard and motionless in static equilibrium. But, maybe you're not the most coordinated bloke out there, or I don't know. Maybe you just, we're getting on from too far to the side, and you put your foot on, you're at an angle, and then you go to get on it. What's the skateboard going to do? It's going to kick out. It's going to roll away from you. And that's this situation here. Even though it did have the potential to be in static equilibrium, the orientation of the reaction vectors were such that it caused an instability. Here, sum of forces in the y, it has no problem. Sum of forces in the x, however, there is no way for it to be resisted. So that's one type of statically determinate structure that is still unstable. Okay? Here's another one. If your reaction vectors are all concurrent, and meaning their lines of action act through a single point, and an applied force does not. So this is like a skateboard inside of a concrete ditch, and you're like straddling the sides of the ditch. So the board's wheels are touching. One's on one side of the ditch, one's on the other side. If you stand right in the middle of the skateboard, you can balance in there. But if you try to get on one side, you put your right leg on before you put your left leg on, the whole skateboard's going to flip out of the ditch. You're going to flip over and land in the ditch, and everything's going to, everybody's going to be laughing. And that's what this is. This is a case of concurrent reactions with a non-concurrent applied force. If you sum moments about point C, you get no moment generated by any of your support reactions, but your applied force generates a moment, and that's the big bummer. So even if there are just the right amount of reaction vectors to make a system statically determinate, the arrangement of them can create instability. This can happen when the reactions are all parallel, like up above, but the loads are not, like here, or when the reaction vectors are all concurrent, but the loads are not below. There are other possibilities, but these are really the main ones.